Hey everyone, welcome back. And today let's solve another Leetcode problem. So today let's solve a design graph with shortest path calculator. So we're given a directed and weighted graph which has n number of nodes, and for each node we're given the source, the destination, as well as the cost of that particular edge. And then we're expected to implement this graph class, and it has these three methods. So we're expected to initialize the object with n number of nodes and the given number of edges, and then we need to support the add edge operation. So we'll be given an edge with the destination, the source, and the cost, and we need to take care of that. And the main part is the shortest path method, right? So for this we're expected to return the minimum cost of a path from node 1 to node 2, and if there is no path with exists, then we're just going to return -1. So that's what we're expected to implement. And if we talk about the conditions, there can be 100 number of vertices and n times n minus 1 number of edges, right? So that's basically like n square number of edges. And one important point is that this graph will never have negative weights, right? So that's different scenario, and there are other algorithms to take care of that. So we don't have any cycles, which is also given over here, and there is no edge with the negative weight. So these are two important points. Now implementing the graph, we're using the adjacency list representation, and add edge is also a trivial operation. The main part of this question is the shortest path method, right? So we'll be using the Dijkstra's algorithm in order to implement this particular method. And yeah, let's now talk about that algorithm, because that's the main part of this question. So let's hit the drawing board and try to understand the Dijkstra's algorithm, and then we're going to use it for implementing the solution to this problem. Alright guys, so now let's try to see an example and understand the Dijkstra's algorithm. So a Dijkstra's algorithm is basically a single source and shortest path for all the vertices. So we're given a source vertex, right? So which is 0 in this case. And if we run this algorithm, we will be able to find the shortest path, or the minimum cost path from this vertex to all the given vertices in the graph. And for that particular question, we just care about the final destination vertex. So yeah, we'll be definitely, because we're finding it for all the vertices, we'll be able to find for 4 as well. So how this basically works is we have a priority queue, and we'll be using this to find that particular vertex, which is the one with the lowest cost, and we're just gonna then pop it, and we're just gonna visit all its neighbors and see if we're able to find a small a path with a lesser cost than what we have already found, and then we're gonna update it one by one. And for this question, so when we start off, we have all the we just initialize the cost to reach for all the vertex as infinity, and then we're just gonna find it for a lower and lower value possible. So let's see a run of this algorithm. So we're gonna start off with 0 itself, and we're just gonna push the value 0, 0, and this particular tuple is of the format cost and vertex. So it takes a 0 cost to reach the vertex 0, because we're starting from that, and then we're gonna visit all its neighbors, and we're just gonna see what is the cost to reach those neighbors, and we're just gonna push it in the priority queue. So for this example, let's see the neighbors of 0. So we have 1, right, and the cost to reach 1 is just this particular 1 itself. So we can reach 1 with a value of 1. And by the way, we have already popped this value, so we're just going to delete 0, 0. And so we're able to reach 1. Let's see other neighbors. Also, we're going to update this value as 1, because we found a smaller value to reach 1. Fine, so we're done with 1. Let's see other neighbors which we can reach from 0. So we have 2. We can reach 2 from 0, and the cost for that is 4. Is it lesser than what we already have the cost, which is infinity? Yes, we do. So we're just going to update it as 4, and we're going to put in the cost was 4 to reach 2. All right. Any other neighbors? No, we only have these 2. So that's fine. And now let's try to pop the smaller value from the priority queue. So we're just going to pop this value, which is 1, 1. So now we are at this vertex, which is 1, right? So now let's see for its neighbors. So from 1, what all are its neighbors? So we only have 3. And what's the cost to reach 3? It's going to be 1. It's going to be 1 plus 2, which is 3. And is it lesser than what we already have found out? Well, yes. So we have 3 as the cost to reach 3, and we're gonna just put the value 3 as the cost to reach 3. Cool. So we have processed these nodes. So we're done with 0. We're also done with 1. And now let's try to pop the other value from the heap. And this is going to be 3 itself. So now we are at 3 at this moment. So now let's try to search for all its neighbors. So for 3, we can reach to 4. Right, and what's the cost to reach 3? 4, that would be the cost which was to reach 3 plus the cost to the edge to reach 4. So that's gonna be 1 plus 2 plus 1, which is gonna be 4. So we can reach 4 with a cost of 4. All right, so we will just gonna add 4 as the cost to reach 4. And any other neighbors? Well, not really. So we're done with processing 3, and yes, we're done with processing 3. Now let's try to solve and see for other nodes. So this time we're gonna pop 4 comma 2. Now why 4 comma 2, not 4 comma 4? So the reason for that is since the first value is same, so heap will now try to look out for the second value in the tuple, which is 2, and here it is 4 in this case, right? So just to show you, we have 2, we have 4. Now the smaller one is this, so this is gonna get popped out, right? From 2 we have just one edge going to 4, and the cost to reach to 2 was 4, and the cost to reach 4 from 2 would be in this case 4 plus 3, so which is going to be 7. Now we see that we just compare it with the value which we already have, right? So we have a smaller cost to reach 4, which was 4, and since 7 is greater than 4, then we're not going to do anything because we already have found a path which had a smaller cost to reach 4. So we're just gonna ignore this particular edge or this particular path, right? So because that's the point on using the heap. Okay, we are finding the minimum cost to reach the vertex, so this is going to be ignored, and yeah, we're done. We won't really update it because we have already found the smaller value to reach till 4. So we're done with this, and now let's try to pop another value from the heap, which is going to be 4 comma 4, and we're done with this, right? And now we are on this particular edge, but we don't on this particular vertex, but we don't have any outgoing edges from 4, so this is also going to be processed. So now we have processed all the different vertices. So this was 0, sorry, so this is going to be 0 because we started from there. So and this is the smallest cost to reach all the different vertices, and for this particular question we wanted it for 4. So the smallest or the minimum cost for 4 is going to be 4. Now as you can see in this question we have multiple paths. Okay, so we could have taken this one, 4 plus 3 to reach here, which is going to be 7, but we ignored this. We rather took the shorter one, which is this path, and that's the thing about Dijkstra's algorithm. It's the benefit of using the priority queue or the heap, so that we find minimum cost to reach a particular edge, and also it calculates for all the given edges the minimum path to reach out there. Alright, so now let's quickly talk about the time and space complexity of the solution. So now talking about the time complexity, so the main work is done in the while loop, which will run until the Min-Heap is empty or all the reachable nodes are processed. And in each iteration, we pop the node with the minimum distance from the Min-Heap and update the distance for its neighbors. So for each edge, we can perform constant time operations. And in the worst case, each node and each edge are processed once. So that results in the time complexity of big O of V plus E times log of V, and this complexity comes from the use of the min-heap or the priority queue, and as we know, V is the number of vertices and E is the number of edges. And talking about the space complexity, so we're using the distances dictionary and min-heap. So the dictionary requires a big O of V to store the distances for each node, and the min-heap can have at most all the nodes in the graph, so that leads to big O of V space. So the overall complexity is 2V, so that's going to be big O of V because we ignored the constant values. So this is the time and space complexity for these problems, and these are the typical for the Dijkstra's algorithm, which use the Min-Heap implementation. And there's also one where we use a Fibonacci heap, and the kind of complexity can be improved using that, but that's a bit complicated implementation in itself. So this is going to be enough for this particular problem. Now let's hit back the question and write the code. All right, so now let's start implementing the solution to this problem. So first we're gonna do the initialization part. So self dot, let's take the variable self dot nodes, which will be n, and then let's implement the graph, and that's going to be graph, and we're using I for the node, and it's just going to be an empty dictionary, and for I in range of n, right? So that's it. And now let's try to populate the graph with the edges and the cost. So we're going to have source, we're going to have destination, and cost in edges, and self dot graph of source and destination. That's going to be the cost. And that's it for the init part. Now let's come to add edge, and that's going to be similar to the previous this part which we did right over here. So let's just copy this out. Let's just put it over here, and let's just make some changes to this. This is going to be source, destination, and cost, which will be the edge which we were given in. And then we're gonna just do this thing. Right, so add edge is done. Now let's come to the shortest part. Now this is the main part of this particular question, and let's just initialize the infinite variable. And now let's just do distances, which is gonna take hold of the distance for all the edges, or sorry, for the nodes, for node in range of self.nodes. Right, and now we're at the source vertex, right, which is node 1. So for that, the distance would be always 0, because we're trying to find the distance starting from this node. So this is going to be 0 in all the cases. And now we're going to use the priority queue or heap, and we're just going to initialize it with the value 0 and node 1, and the format is it's distance, the first index, okay, and then we have the node. Okay, so node 1 is the node and 0 is the distance, and this is going to be the initialization for over here. And now let's use the while loops, and we'll just keep the condition on heap, and yeah, we're just gonna pop things one by one and then just update the distances. So we're gonna use the heap queue, which is provided by Python for operations on the heap. So we're just gonna pop the smallest pair from the heap, and if the current distance is greater than distances current node, then what we're gonna do is we're just gonna continue, because we already know a smaller distance, or we already have a smaller value, so we're just gonna ignore this for now. Now let's iterate over the neighbors of this particular node, because then we're just gonna check each one of them that whether we have a smaller path to our destination via these nodes. And let's just go over this, the items, and the distance will be current distance, because yeah, we just reached to this node using the current distance, so we're gonna just add that. And then we have the weight, which is the cost we incur for traveling to that particular node. And if the distance is less than distances at neighbor, so what it basically means, this if condition means, is that we've found a smaller path or a smaller cost path to that particular node. So we're just gonna update that in the distances, yeah, that particular list, and it's gonna be distance, and then we're gonna push it back into the heap, this new value, and it's gonna be distance and neighbor, which is the node. Right, now I guess we're done, and then we're gonna just return distances at node 2, which is the destination node. And if node 2 is not equal to infinity, else we're just gonna return -1. Let's make it a little bit more readable. Okay, so I'll just use a variable for that. Let's put it in answer. So if answer is not equal to infinity, then yeah, we do this, otherwise we return -1. So why we're doing this is because if it's infinity, that means because that's what we initialize it, right? That means we were not able to find a path to this particular node. So as given in the question, we're just gonna return -1 for that. So if no path exists, return -1. So just to satisfy that condition, we're just gonna return -1. So yeah, that's the code for this problem. And as we discussed before, there can be repeated values for a particular node. We might have two different values, but that won't really affect. Okay, so we won't really have any problems because of that. There can be repeated, like we might visit a particular node twice, but yeah, the distance would be definitely different, or the cost to that particular node would be different. Similarly, for there can be multiple nodes which we can reach with a similar cost. So but yeah, these repeated values won't really have any effect, because one particular pair of distances node that is going to be unique. So for suppose we have a distance of 5 and node is 2, so that's fixed. We won't have another node of distance with distance 5 and another. So repeated values won't be there. So it basically would work if you're visiting the node twice, but yeah, in all the cases the cost would be different. So now let's try to run this quickly and see if this works. It should work. Cool, perfect. So now let's try submitting this. Hopefully it should work. All right, so yeah, we have the solution accepted. So that was it, and I hope we explored the Dijkstra's algorithm today, and this would be really helpful for you. So thank you so much if you were here until this point in the video, and consider giving this the channel subscribe, this video like, and share it with your friends and all those who you think would be helped by this video solution. Until then, stay happy, stay healthy, and I hope to see you very soon in another video. Goodbye.